of once you've made it, it's actually somewhat straightforward to understand. Getting to it is tricky. And how they discovered it the first time is absolutely amazing. But once you've made it, it's a lot more straightforward to understand. So, in a magnetic coil, when you have a round electrical coil, you have electrical current flowing in that coil. And if you have a conductor, if you have a metal inside that coil, and this is called Lenz's law in one of the Maxwell equations, is that as you have electrons and you have current flowing in that coil, an equal and opposite electrical current is induced in a piece of metal nearby. This is the same thing that happens in a transformer, where you have a primary on a transformer and you have electricity flowing it, and you have a secondary where electricity flows exactly the opposite direction. We use this every day in our lives. And so in this condition, you have a conductor, an electrical conductor where current can flow, and you have an electrical current flowing on the outside, electrical current flows on the inside. And in that case, now I've described two pieces of metal. Now, let's go one step further, and that inner conductor is not a piece of metal anymore. It's one of these high-temperature gases, this plasma, this charged particles. So now you have electrical current flowing in the plasma. And this is really, really interesting. We talked about these charges moving back and forth. Well, moving electrical charges is current. So in every plasma condition we've talked about, the tokamak, the theta pinch, the stellarator, there's electrical current flowing in the plasma. But in the field reverse configuration, you have a lot of electrical current flowing in the plasma, massive amounts of it. And that's the key. So you have the center core where electrical current is flowing in this transformer, if you want to think about it, primary and secondary. And here's the craziest part of it. This electrical current, how did I describe a magnet? An electromagnet is a loop that has electrical current flowing in it that generates a magnetic field. And for a theta pinch, and for a mirror, and for a tokamak, in that magnetic field, the plasma gets trapped. But in an FRC, this electrical current is the plasma. And that plasma then generates its own magnetic field. And it's then trapped on its own magnetic field.
That's fascinating.
And that's the key. And so in your tokamak, in your donut, and in your funky donut, your stellarator, you make the magnets and you trap your plasma in it. In an FRC, you make the plasma, which makes the magnets, and it traps itself. And the craziest part of this, in my mind, is that we actually see this in nature all the time. If you look at the sun, we see solar flares. And in a solar flare, we've all seen the pictures of the photosphere of the sun and this large arc of plasma coming out. That plasma has current, electrical current flowing in it. And then we see this solar flare rip off of the sun. Mm-hmm. And that solar flare then can flow throughout and continue into the solar system. And for a little while anyway, it makes something called a plasmoid. That plasmoid is, in fact, electrical current flowing in the plasma, generating a magnetic field, and holding it for longer than it would otherwise. And so we've observed these for 100 years. And we've known about these plasmoids for a long time. And there's researchers that have tried intentionally to make them. But fundamentally, that's what we do every day, is make one of these self-organized closed field plasmas.